In attempting to fly from Chicago to Louisville, a distance of 330 miles, a pilot inadvertently took a course that was 10 degrees in error. I sketched out a picture here. So here's Chicago, down here is Louisville, and this distance is 330 miles. A pilot took a course that was 10 degrees in error, so this angle up here is 10 degrees. If the aircraft maintains an average speed of 220 miles per hour, and if the error in direction is discovered after 15 minutes, through which angle should the pilot turn and head toward Louisville? What we want to find is this angle right here. And I can tell, even if this drawing is not perfectly to scale, I can tell that that's going to be a big angle. We're given some information about this side length right here. So let's find out what that mileage actually is. The speed is 220 miles per hour, so miles divided by hours, and the error in direction is discovered after 15 minutes. 15 minutes is 1/4 of an hour. If I don't know that off the top of my head, I can always look at 15 divided by 60, which reduces to 1/4. 220 miles divided by hours times 1/4 of an hour means the hours simplify out and we're left with 55 miles. This distance here is 55. We can try using the law of sines, but what we're going to find is we're missing some information. I only know one angle, which means I really need to know the opposite side length right down here. Let me call this distance d. So I could set this up as the sine of angle 10 divided by a distance d equals the sine of angle theta divided by 330, but that's going to not help me because I have two unknowns. Let's use law of cosines instead. I can't solve for theta directly because I don't know this other side length. So let's first use law of cosines to find this missing side length. I'll set this up as d squared equals the sum of the squares of the other two sides, so 330 squared plus 55 squared, minus 2 times the product of those two sides, 330 times 55, times the cosine of that included angle in the sides that I know. So the included angle, which is also opposite the unknown side, is 10 degrees. On my calculator, I found that d squared equals 76,176.47857. Taking the square root of that, I find that d is just about exactly 276 miles. It's 276.000867. I'm rounding that to 276. All right, updating our picture, we now know all three side lengths. Let's try using law of sines now. Using the law of sines to find this missing angle theta, I have the sine of theta divided by the opposite side length, which is 330, equals the sine of 10 degrees divided by 276. And again, I'm expecting this angle to be large. To solve this, we could either cross multiply or simply multiply both sides by 330. And what I've found is that the sine of angle theta would be 0.20717. Take the inverse sine of both sides, and we end up with theta equals just about 12 degrees, 11.9565. That is not an answer that we were expecting. What we have here is an ambiguous case of the law of sines. I know that this angle is supposed to be big, but a 12-degree angle is very small and would represent a very sharp turn on the part of the pilot. Since this is an ambiguous case and we haven't covered those in depth, I'm going to jump back and use law of cosines again in order to find that missing angle. I've erased our other work and just kept our erroneous answer using law of sines. And now we're going to set this up using law of cosines. I want to find this missing angle, which means I need to take the cosine of that angle. That means on the other side of our equal sign, we're going to start this with 330 squared equals the other two sides squared, 55 squared plus 276 squared minus 2 times 55 times 276 times the cosine of that angle theta. We have to work to isolate the cosine of that angle. Since 55 squared and 276 squared are just added in, I'm going to subtract them out. I end up with 29,699 equals negative 2 times 55 times 276 times the cosine of theta. Since that is multiplied in, I'm going to divide it out. And if you're doing this in your calculator in one step, make sure you put parentheses around that entire denominator. You're dividing by all of that. In fact, I encourage you to just do this whole problem with me to make sure there's no computation errors on your calculator. We end up with negative 0.978228 equals the cosine of theta. To solve for theta, I'm going to take inverse cosine of both sides. So inverse cosine of that number there equals just theta, because inverse cosine of cosine is theta. And we finally found theta equals 168.022 degrees. I'm going to round that to 168 degrees. That's the angle that the pilot has to turn. Notice something cool here. We haven't talked much about the ambiguous cases of the law of sines, but notice 180 degrees minus 168 degrees results in 12 degrees, which is what this angle is very, very close to. But wait, there's more. I've been talking about this angle 168, the angle we called theta, but really that's not the angle the pilot is turning. If we think about the pilot going straight, this bearing, before they found out the error, the pilot is making a great big turn, but it's not going to be a 168 degree turn. They're going to be deviating from that 168, which means if this angle is 168, they are just going to continue on straight. And so we want to find the supplement to angle 168. And we can do that because we know that these two angles together are 180 degrees. 180 minus 168 equals 12. The pilot will make a 12-degree turn in order to fix what was originally a 10-degree error. This doesn't mean that the law of sines in that ambiguous case suddenly works, because we were trying to solve this angle right here. This angle is demonstrably not 12 degrees, but its supplement is.